Okay, so today I'll be presenting homework 6, parts 1, 2, and 3 of the adiabatic flame temperature. So let's get started with the equation right here, the chemical equation. So with this flame that we have, we're going to need our fuel, which is methane, and then we're going to need our oxidizing agent, which is oxygen. So we have those two right here, and then we're also going to have nitrogen in the reactants, because we can assume that the air that we breathe isn't all oxygen. So then we're going to have CO2 in our products, N2, nitrogen again, and then H2O. So now what we need to do is balance the equation. So what we can do is 2 moles here, 2 moles here, and then we need to understand that there's 79% oxygen, or 79% nitrogen to 21% oxygen in the air. So we need to put that ratio in here. And then we need to also understand that where there's oxygen, there's going to be double nitrogen. So we'll have 2 more moles there. So for the first part, this right here is a perfectly balanced equation, but in real life, you're rarely going to get that. So what we did is account for 20% excess oxygen. So we're going to have to calculate that into the moles. So right here, it's going to become 2.4. It's going to, once again, happen to the nitrogen here, and then right here. And then we're also going to assume that, well, not assume, but there's also going to be excess oxygen that comes out in the reactants. So we'll just have 0.4 moles of O2 over here. And there is our balanced equation with 20% excess oxygen. So now what we're going to do is use the energy balance equation to find the adiabatic flame temperature. So we're going to start off with derivative of mass times internal energy plus potential energy plus kinetic energy equals, we have, so some sort of heat, or some amount of heat, not some sort of heat, some amount of heat plus some amount of work, or multiply that by the enthalpy plus potential energy, or gravitational potential energy, and the kinetic energy inside the system times the change in mass inside the system. And then we're going to subtract the enthalpy plus gravitational potential energy plus kinetic energy outside the system times the change in mass outside the system. Okay, so in order to solve this, we're gonna want to make it a little simpler. So we can make some assumptions about this, starting here. So we understand that this is a state system equation. So basically, there's not going to be too much more being produced that is put in, or too little that's being put in. So we can consider this to be 0. Then there's not going to be a lot of change in heat. So this is going to be 0. There's not going to be any stirring or mixing, so our work is going to be 0 as well. And then finally for so gravitational potential energy, and kinetic energy, the change in energy from, say, the bottom of the Bunsen burner to the top of the flame is going to have such a minimal effect on the outcome compared to the energy of the whole thing that we can just disregard it. So we can make this 0, we can make our kinetic energy 0, and then there's our equation. So now to simplify it, we have our enthalpy in times our change in mass inside to our enthalpy outside, change in mass outside. Okay. So now we're going to change our enthalpy equation a little bit. So we can do our enthalpy inside is going to equal the summation of species I times the moles of species I times the enthalpy of species I. This species being, if you want the heat inside, then you're going to use these reactants, and then if you want the enthalpy outside, you're going to want this species. So now we need to find our enthalpy. So what we're going to do is put our enthalpy here. I forgot to mention that according to T temperature, because you'll see. So what we have is the enthalpy, species I, the temperature is going to equal the heat and ideal gas temperature. So that ideal gas temperature is going to be 298.15 degrees Kelvin. And then we're going to add this to the integral of the specific heat capacity at ideal gas temperature of an ideal gas. So now we need to find this integral. I don't know how to do this on my own, so what I did is I used ChemCAD to find the equation, and it came out to be this. So we'll have A plus B, C over T equals the sine of C over T all squared plus D E over T times cosine of E over T all squared. Okay, so now that we have that, we're going to plug it back in to our integral right here. So we'll just make it easier on ourselves. Do this. Now, what we need to do is we need to find the integral of this so we can get our enthalpy. And then we can plug that back in to this equation. So what I did is I went on Wolfram and I plugged this in. And so what it came out as is so A times T plus B times C over tangent of C over T minus D times E tangent E over T. Okay. So now, all we have to do is continue to plug this back in like I did up here. So we have our integral now. So we're just going to add this heat, and then what we're going to do is put in brackets so that we know it's the moles times all of this times the summation of species I equals the enthalpy in the system. So there's our first equation, and then our second equation, we're going to need the enthalpy outside the system. So it's just same thing, just now it's outside. So we'll have our, plus BC over tangent C over T minus DE tangent E over T 298.15. Okay, so these are our two equations, and this is what my partner Griffin is going to use to code the and find out the adiabatic flame temperature.